Okay, let's go ahead and get started. Welcome everybody to CS and or ECE 374. My name's Jeff. This is my first time regularly lecturing in this room, so you'll forgive me if there are the occasional AV hurdles. In case people haven't already figured this out, this is one of two completely independent sections of 374 being offered this semester. Mahesh is right at this very moment starting his lecture for Section B over in the Natural History Museum. In case there's any uncertainty about this, these two sections are being run entirely independently. Different lecture schedules, different labs, different homeworks, different exams, different grading curves. It's exactly as though we were teaching in two different semesters and one of us has a time machine. While I don't have a strict attendance policy, all my lectures are being recorded. I believe all of Mahesh's lectures are also being recorded. So if you're from Mahesh's section, you're welcome to sit in, but keep in mind I may say things that Mahesh doesn't like, and that if you do them and Mahesh gives you lower scores, it's not my fault. We don't anticipate, because both sections are completely full, we don't anticipate running a waiting list. We don't anticipate allowing students, except for extreme circumstances, to switch between sections because you're meeting at exactly the same time. Switching from one section to the other isn't going to help your schedule. If you're registered, congratulations, welcome. If you're not in, if you're not registered at this point, I have no good news for you. In past semesters, we've run waiting lists, and inevitably what seems to happen with waiting lists is that 2, 3, 4, 5, 6, 7 weeks into the semester, there's still people on the waiting list who are extremely stressed out by the fact that they don't know whether or not, and we don't know whether or not you can get into the class. We've expanded the enrollment to almost 600. At this point, we feel fairly comfortable saying anyone who hasn't gotten in can wait a semester. That said, if you absolutely need this class to graduate on time, meaning you are a CS major and you want to graduate by December 2018, or you are a computer engineering major and you want to graduate by May 2018, send me email and we will figure out how to squeeze you in. Okay. This is the website. Everything will be posted here. In particular, you can already find homework 0. Homework 0 is due 1 week from today. Homework 0 will be submitted. You'll submit, your own PDFs on Gradescope, which you may have used in other classes. Gradescope is an external website, so that means because the university doesn't have a contract with it, we cannot require you to use your real name and your real email address. So you're welcome to sign up on Gradescope using whatever alias and whatever email address, including burner addresses, you want. Please don't everybody sign up as Benedict Cumberbatch. There'll be a separate web form to tell us who you are so that we can actually associate your work with your university identity and give you a grade. There are very good reasons why this federal law is in place. This is an external entity. We don't really know what they're going to do with the information. And there are occasionally students who have very good reasons not to want to publicize the fact that they're here. Same thing goes for Piazza. You can sign yourself up using whatever alias and whatever email address you want. Again, please don't everybody sign up as Benedict Cumberbatch. We're not generally going to ask you for your identity here. It doesn't have to be the same as on Gradescope. But if we do notice people who are being fairly strong contributors on Piazza, we may give you a bit of extra credit. We might consider offering you a course assistant position next semester. In fact, some of the CAs that we recruit every semester are always the people who participate and help out a lot on Piazza the semester before. That is the website, and it says there are two sections. If you get lost, there's an A or a B in the URL. Everything is already up, in terms of what we expect to be covering, and I'm not sure what else we need to actually talk about here in terms of Administrivia. You'll notice office hours are not actually listed up here. That's because we haven't figured them out. If people have questions for me, I will be out in the lobby immediately after class today and on Thursday. All right, so there are a couple of policy things that I want to talk about before we get to the actual course content. Most of these, hopefully, are familiar and therefore boring, and so those of you who want to pull out your phones and play Getting Over It for the next 5 minutes, please feel free. So one thing that may be different about this class than other classes that you've been in is we allow you to do homeworks in essentially arbitrary groups. You can submit group solutions after homework 0. Homework 0 we want you to do by yourself. But in groups of up to 3 people, and you can work with anyone you want, and you can use any resource at your disposal. You can use any textbook, the internet, Stack Exchange, Piazza, office hours, your older brother who took the class 3 years ago, whatever. Provided that you follow 2 rules. Rule 1 is you write everything in your own words. That means, in particular, if you stumble across old homework solutions that I wrote, that you write them in your own words rather than parroting my words back to me, because the point of the homework is to test your understanding of the material, not your ability to press Control-C, Control-V. The second is you cite your sources. If you get help from your older brother, you say, I got help from my older brother. If you got help from a group of 20 people that meets in the lobby of ECE every Tuesday evening, you say, I got help from the group of students that meets in the ECE lobby every Tuesday evening. The only sources that you don't have to cite are my lecture notes and me. And prerequisite stuff we assume you know. Okay? So the reason that we try to be this liberal about this is that I believe the homework is actually where you learn. This is where the class actually happens, is when you roll up your sleeves and dig out your pens and you actually start writing and figuring things out. What happens in this room with me in front of it is probably the least important part of the class. My job here is to give you examples, to present some initial definitions, to try to provide a little bit of intuition and background, to convince you that the things we're doing actually make sense mathematically, formally, logically. What we do in the labs is the TAs and the CAs who are running the labs, by the way, the TAs and CAs who are here, could you stand up, please? So Philip is our lead TA, so you may see him more than you see other people. I know there's at least one CA also in the room, but you don't have to stand up if that's okay, if you don't want to. The point of the labs is the TAs who are running the labs will try to walk you through the process of solving the kinds of problems that you will see in the homeworks and the exams. The point of the labs is not, here's a problem, and then 20 minutes later, here's the solution. Because the solution to that problem isn't really the point. The point is to help you solve the next problem, and the next problem, and the next problem after that. Which is also, to some extent, the point of the homework. And then to get feedback while there are people in the course staff who are in the room who understand the material better. Same with the homework. The point of the homework is for you to practice with the material and then get feedback on your mastery, your ability, your comfort level with the material. And we cannot give you that feedback that will help you learn if you are not honest with us about what you understand. So when we talk about citing your sources and we talk about writing things in your own words, we do that so that you give yourself the most opportunity to get honest feedback on how you're doing with the material, so that when it comes to the exams, which are 70% or more of the grade, you can do as well on those as possible. I'm sure you know very well this is a difficult class. It really requires sustained practice, sustained attention. Homework is due every Tuesday evening. Don't start Tuesday afternoon unless you're starting on next week's homework. Give yourself lots of room, ask lots of questions on Piazza, ask lots of questions in office hours. Our job is to give you the tools you need to succeed, which all of you can, otherwise you wouldn't be here. Okay. The second thing that I know some of the classes do this is the I don't know policy. So the high-level policy is at any time for any question that isn't extra credit, you can answer I don't know and get 25% partial credit. In particular, if you have a 4-part homework question and you answer parts A, B, and C, and you write I don't know for part D, you'll get 25% for part D, and we'll grade parts A, B, and C separately. That's the level of resolution we're going to go at. So we don't want to say you write half and say I don't know how to do the rest. That we don't want to count. And the idea here is to sort of bypass the tendency for some students to just babble, hoping that we'll pick out a couple of words here and there and say, oh, you use the words dynamic and programming together. That's worth a point. No, that's not worth a point, because it doesn't actually demonstrate any understanding. What it's not meant to do is to prevent you from showing us what you can do. It really is there as an outlet for, I'm just completely lost. I'm going to throw in the towel. I don't know. If you write something, even if it's part of the solution that's correct, you'll get partial credit. And our intention is we very, very, very easy to get partial credit that's worth more than I don't know. Okay. Now, 2 other things about this. One, on homework, it doesn't make sense to turn in I don't know for an entire homework problem. And the reason for that is the way homework is credited in the final grade. Every homework problem you submit is worth 1% of your grade, or 1.25% of your grade. So there's a minimum amount that you need to turn in. It's about half of the homework. And then beyond that, it's only, it's to your benefit to practice and get feedback, but we're not seeing this as a vehicle for points. So if you're sick and you need to miss homework, okay, fine. The exams will count a little bit more. If you need to miss, your dog ate your website or whatever, fine, things happen. We'll let it go. It's not such a big deal. It just means the exams will count slightly more. And so what this means is if you turn in an I don't know and you get 25%, that 25% will count in your homework average. If you don't turn anything in, it won't. And so if your exam average is above 25%, averaging in a 25% lowers your grade. On the other hand, if your exam average is below 25%, you are in serious trouble. Something is very, very wrong. You need help. And that's really what I want you to think of the I don't know policy is. It's not just a signal to us that you're admitting you don't know the answer. It's also a signal to yourself that this is something that you need help with. Please ask us for that help. Similarly on exams, it's very easy for people to feel overwhelmed and just say, I don't know if this is going to be worth more or less than I don't know. Chances are, if any part of it is right, it's going to be worth more. If you find yourself just sort of going, screw it, I don't know. Screw it, I don't know a lot, that means something is wrong. Please ask us for help. If at the end of the semester you've done this too many times, we're likely to treat you as an outlier for purposes of computing the curve, because you're not really engaging with the class at that point. So more than a certain threshold, you risk taking yourself out of the curve. All the people who actually answered the questions will determine the letter cutoffs, and then we'll slot you back in wherever you go. Okay. So eventually, doing this too much can hurt you. All right. The last thing that I need to say, and again, I apologize to the vast majority of you for whom this is not even a thing that needs to be said, but usually there's about 0.5% of any class that this is an issue for in any given semester. We really are quite serious about you citing your sources and writing things in your own words. Because we really think of it as our job to give you honest feedback, and we're kind of have an agreement that your part of that arrangement is that you will show us honestly what you can do. If you violate that trust, then you're kind of screwing it up for everybody else. So there's a long web page about exactly what we expect. Cite your sources, use your own words. In particular, yeah, quoting stuff is nice, but if you quote sparingly and cite your sources, I will not be flattered by you parroting my words back to me. I'll be insulted. And there's some stuff about what happens if you get caught. And in particular, there's some stuff here about working in groups. These things get really complicated when there are 3 of you turning in a homework and one of the 3 of you plagiarizes. I'm not going to walk through the various scenarios here, but let's just summarize by saying we've thought hard about this. We have several examples of what might happen. The short version is don't let other people in your group do the homeworks without you looking at it. By turning it in with your name on it, you are pledging that you at least understand and agree to submit this. So that if later there's a problem, you're responsible for some of it, even if you weren't the actual author. And I think with that, I need to stop and answer any administrative questions. Those of you who are frustrated with getting over it should stop now. Yes, there's a question in the back. We are still working out the office hours for this week. I'm hoping that we will get those set up, have at least some office hours starting tomorrow. So watch the webpage. Meanwhile, you can get help by posting on Piazza or talking to me after class or talking to the TAs after labs. Two hours ago. So the question was, when was Homework 0 coming out? Yes, another question over here. I'm sorry, I'm having trouble hearing the question. So your homework group needs to be all people from this room, not Mahesh's room, because Mahesh is different homework than me. Aside from that, I don't care. So if you're in the same lab section or different sections, doesn't matter. If you use a different group for Homework 0 Problem 1 and Homework 0 Problem 2, it doesn't matter. Right? So the group is defined by, when you submit on Gradescope, you say who submitted the homework. That's the group for that homework problem. So it's entirely up to you if you want to switch, if you want to move around, or if you want to stay. If you want to work by yourself, that's okay too, although generally we kind of discourage it unless you're really comfortable with the material. But no collaboration with Section B because they're doing different things. Yes? 3 or less. 3, 2, 1, or 0. And everyone who submits will get credit. I will give extra credit if anyone can figure out how to submit homework with a group of 0. But if you do, every one of those 0 people will get credit. Yeah. So at the end of the semester, we will do the matching between Gradescope identities and registered students. In practice, very, very few people want to do the work if they're not actually registered, so we won't notice the 1 or 2 that do. No, it would be a group size of whoever submitted it. I suppose I should say, don't submit with a group with somebody who got an A in 374 last semester. We'll notice that too. Yeah. One person submits the homework and then lists the Gradescope identities of the other people in their group. Please be careful about not using real names if the people you're working with aren't using their real names on Gradescope. Yeah, last administrative question. Yeah, if you are using your real name and your Illinois EDU address, you don't need to separately fill out the form. We already know who you are. We're not going to be, if you're using your Illinois address, we'll assume that's who you are. Okay. It's entirely up to you. There are good reasons why some people might not want to use their real name. I've met students who are hiding from abusive parents or abusive spouses, where it really is important that no one know that they're here. If that's not you, it doesn't matter. Right? It might be easier to use your real name just so your group mates don't have to figure out, now, what do you call yourself again? All right, but we can't require you to do that. All right, so let me hopefully have an Apple Pencil now with a bit of power on it. Well, okay, that's better than nothing. And I will get set up here. Good. That's not what I wanted to do at all. As I said, sorry. I think I just... No, I don't want to use the Apple TV and noise. All right. So, first thing I want to say a little bit about what this class is about, which I suppose we should just summarize as why are we here? And I'm sure for a few of you, the short answer is we're here because this is a graduation requirement. But that just puts off the question, why is this a graduation requirement? So what the class is about is sort of theoretical computer science. And the question that we're going to ask is, what can be computed, right? So if you've taken a bunch of other computer science classes, we're saying, here, make this computer do this thing. Make this, listen to some network sockets. Make this, implement desert golfing or something. Implement Facebook. Implement Eclipse. You've built systems, you've built programs that can do things. But the question that we're asking ourselves in this room is, well, first of all, at a very basic level, what can be computed and what can't? And you may remember some discussion in earlier classes that there are certain things that just can't be computed. And what that means is if I specify the problem as given this particular function, I want you to write a program which can compute this thing for arbitrary inputs. There are simple questions where the answer is you can't do that, and there are also simple questions where the answer is nobody knows whether we can do that or not. So by the end of the semester, we'll be talking about some examples where the answer is no. Most of the time, what we're going to be spending the semester on are things where the answer is yes. And then, backing up in time through the semester, a large chunk of the class is devoted to the design and analysis of algorithms, where the question that is being asked is not what can be computed at all, but what can you compute quickly? What can you build algorithms for that are fast? And if so, how? So if I say, gee, I've got this, this fragment of RNA that I want to match to a gene database, how would you do that quickly, right? And the quickly here is, you know, you can probably come up with some sort of horrible, ugly, brute force way to do things. A lot of things we can do better. On the other hand, there are some things where we can't do better, and we can prove that we can't do better. We start talking about problems being NP-hard or NP-complete. These are problems where we actually have a mathematical proof that there is not going to be a fast algorithm modulo a conjecture that should really be considered a law of physics. And then backing up even further, the first part of the class is really about what can be computed with extremely tight resource constraints. So we're going to be spending a lot of time for the first few weeks talking about finite state machines. And you should really think of a finite state machine as a computer that doesn't have any memory. In particular, you're not allowed to make function calls because stack is memory, which means you're not allowed to do anything involving recursion because stack is memory. And so if you're not allowed to actually write things down or write more than a very small amount down, what can you do? And some of you may have seen finite state machines in the past, and there is actually a fairly rich set of things that one can do with this tight resource constraints. But you can't do everything. And understanding what you can and can't do in this very tightly constrained environment can be very useful. Now, most of you are probably not going to be going out in the real world and working for Facebook and Amazon and building finite state machines for a living. Some of you will, because if you've ever written user interface code, that's what it is. It's a giant finite state machine. But that's not the main point of introducing this material. Some of it is just to get across the idea that there are limitations to what computing machinery can do. But some of it is that we want you to practice in this very constrained environment with thinking very carefully, very methodically, very formally and abstractly, because that's the way computers think. Okay? So if you haven't figured this out yet, you know, a really fun thing to keep in mind is computers are really stupid. They will do exactly what you tell them to do, which is annoying as hell, because figuring out how to actually tell the computer what to do is, well, I mean, that's what computer science is, I'm afraid. It's really, really hard work, and that's what makes this class hard. So we're going to start trying to communicate with these stupid machines by making the machines even stupider, giving ourselves a very limited vocabulary to play with, and getting used to the idea of talking to the machines at this very constrained, very low level. If you are an ECE major, you have already gone through this process once when you started building up from machine code, building up to higher level languages, right? Talking to a regular computer using assembly language is sort of revealing the stupidity of the underlying machinery. It's very mechanical. It's sort of grind, 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 fetch an instruction, fetch the memory, figure it out, store the results, fetch the fetch the da. And so we're dealing with things at that level of simplicity. And the reason you do things in assembly language is not because most of you are going to go out to Twitter or Snapchat and implement things in assembly language, although some of you will. It's because we want to get used to the methodical thinking process before we get to more free-form design of algorithms. The flip side of this is people are clever. Clever is bad. People come up with all sorts of cute insights. Oh, I can just skip ahead and just do this one thing. And you can always tell that you're going to get into trouble because the J word creeps in. You just need to do this one thing. This is, again, just like the I don't know is a signal for I need help. That word just, and it has, you know, siblings, like obviously, clearly, of course. Left as an exercise for the reader, that are clear signals that the thing that is being talked about is probably wrong. I'm embarrassed to admit how many times I have fallen for this trap as a researcher, where I have papers that have bugs in them that can be traced to a single occurrence of the word clearly. So I want you to remember, in some sense, you're talking to a computer. It's stupid. It's not going to understand your leaps of intuition. You have to tell it every single step. And so what we're starting with today is something that is really, really simple. We're going to be talking about strings, sequences of things. We'll call them symbols, but they're really just things. And the reason, we're starting with this simple is just to get used to the idea of exploiting our intuition, but then producing something careful and methodical and formal because we're trying to think like a computer. Computers are stupid. They're also, tireless and methodical. At some level, we want to try to behave like that as well when we're trying to tell the computer to do things. Okay, so I'm going to start by giving some definitions. The thing that we're really practicing here is recursion and induction. They're the same thing. If you think of them as two different things, throw the induction one out and just think about recursion. But everything we're doing is really meant to be sort of exercising your recursion and induction muscles. Nothing I say, none of the content I'm going to say is going to be surprising. And it's very easy to be distracted by the fact, well, why is he explaining this obvious crap to us? We know what a string is. String. Anyone? Yeah. It's an array of characters. Of course. What could be simpler? This is probably the first thing beyond, say, an integer that you ever manipulated with code. But I want to make sure that we distinguish between how we should think about strings abstractly, especially if we want to prove things about them, and how they're actually implemented in the code. And this is something that's going to come up over and over again. How we think about computation is not necessarily the same as how we write about it. Okay, so what is a string? Definition. A string is either nothing or it's an ordered pair, AX, where A is what we'll call a symbol or a character coming from some arbitrary finite set, which we'll refer to as the alphabet. And for historical reasons, sigma stands for alphabet because if I wrote a capital alpha, you would think it was an A. Oh, and where X is a string. Okay? A string is a sequence of characters. A sequence of characters is either nothing or it's a character followed by a sequence of characters. A sequence of students is either nothing or a student followed by a sequence of students. A sequence of flying giraffes is either nothing or it's a flying giraffe followed by a sequence of flying giraffes. Okay? This is a recursive definition. Now, there's an implicit clause in this recursive definition, which is that eventually the recursion has to bottom out. So all strings are finite. I'm not talking about infinite sequences of characters. I'm talking about finite things. Eventually, I have to hit the base case. I'm not going to bother to write that into my recursive definitions, but you just think it's always going to be there. Okay? Now, some notation. Nothing, we normally refer to nothing as the empty string. And we, at least in this class, will abbreviate it with the Greek letter epsilon. Now, I want to be very clear that Greek letter epsilon is not one of the elements of sigma. It is not a symbol. This string, even though it has on the page something that you wrote down, has nothing in it. It's empty. It's right? It's kind of like the empty set, but it's a different type. And then normally, when we're talking about this ordered pair, we're not going to use the syntactic sugar where we open a paren, write the symbol, put down a comma, write the recursive string with all the parens and commas, and then write the close paren. We're normally going to write this either with a little dot, if we want to be extra careful, or just by juxtaposing the symbol with the string. So generally speaking, when I'm talking about strings, I'm going to use uppercase letters, but under the hood, what this actually stands for is this. This is an ordered pair whose first element is S and whose last element is tring. That's an ordered pair whose first element is T and whose last element is ring. That's an ordered pair whose first element is R and last element is ing. That's an ordered pair whose first element is I, last element is ing. That's an ordered pair whose first element is N, last element is G. That's an ordered pair whose first element is G and whose last element is the empty string. Okay. That's what a string is, at least in a way that allows us now to prove things about strings. And at some level, you know, the only reason for having this kind of recursive definition is so that we can reason about these things formally. It's a little bit harder to do that with just arrays. Okay. The set of all strings over an alphabet sigma, I'm going to write that as sigma star. There's actually a meaning here. It doesn't matter what it is for now. Just think of that star as meaning the set of all strings in this alphabet. The set of all finite sequences of things in sigma. Okay, so now I'm going to do things that are even, you know, stuff that you'd want to do with strings. One of the things that you might want to do with a string is figure out how long it is. But if I want to prove things about the lengths of strings, I need to match my definition of length to my definition of string. Right? I can't just say it's the number of symbols. That's being clever because I haven't defined what number of symbols means. So I need to actually write down a formal definition. So I'm going to do it this way. I'm going to use absolute value to mean length. And now the definition of length has two cases because the definition of string has two cases. So I'm going to write down the two cases before I even get started. So one possibility is that the string is empty, and the other possibility is that the string is not empty. It starts with some symbol A and ends with some string X. Now I'm going to ask you to tell me what goes here. 0, good. And what goes on the next line? 1 plus the length of X. Duh. What else could it possibly be? Okay. Let's try another one. Concatenation. Write one after the other. So the idea is that I want to say things like foot concatenated with ball, and I'll write a big dot here to denote the actual function. This is the string football. Now, we kind of know how to do this in one special case. If the first string is actually just a single character, then gluing a single symbol in the front of a string is, well, it's the definition of a string. So we can build strings by sort of gluing in one character at a time on the left. What we want is to build up a mechanism for gluing together strings in larger chunks, or in particular being able to glue one character on the right. And it's completely obvious what this means, but to a human being, but we're not trying to explain this to a human being. We're trying to explain this to the stupid proof fairies. And so we need a recursive definition that will mirror the recursive definition of string. There's a bit of a problem now. I've got two strings, W and X. How many cases am I going to need? 4? I mean, B could be empty or not. X could be empty or not. Well, let's try to think about, build some intuition here. Let's start by asking, what's the empty string concatenated with the empty string? What do you get when you put nothing and nothing together? Good. Almost everybody got that except for the people who actually said something. Okay? Nothing. No, I don't want to discourage people from answering questions, but feel good about yourself. Everybody answered that question correctly. Okay, good. So what do you get if you glue nothing to a non-empty string? You get the non-empty string. So if W is empty, it seems I always get X. Okay. What about the other direction? What do I get if I glue something non-empty onto something empty? You get whatever the first string is. And the last case is the one that I have up at the top, where both strings are non-empty. Okay, so looking at the cases for the input doesn't really seem to be helping me all that much, although I seem to be able, at this point, to write at least, I can write x if w is the empty string. So maybe we can run with that and say, well, what if x is, what if w isn't empty? And I don't want to say ax there, because x is already bound to something. So I'm going to call the tail of wy instead. What should go here? Well, what should go here is the definition of a string. And the way that you write down a string is you specify what's the first character and what's everything else. So if w starts with an a, what does w.x start with? An a. And then what does w.x end with? Yeah. Right. It's y concatenated with x. So when I put foot and ball together, you should really remember that every string is an ordered pair that comes with a head that's a single character and a tail that's another string. And what I want in the end is to specify what the head is and to specify what the tail is. And I've done that here. The head is the same as the head of w if it exists. The tail is the tail of w dot with x. Okay? All right, good. So how many of you have ever programmed in something that smells like Lisp? Okay, all of you are insanely bored because you've all seen this. This sort of ordered pair thing is just exactly a Lisp's internal representation of lists. This kind of code that you write, this is a typical functional programming specification for the concatenation function for two strings. If you actually decided to write this out in Python or C or Java or Lua or OCaml or Brainfuck or whatever your favorite programming language is, you would actually do something like this. You would say, okay, what do I write down? When I'm writing down the concatenation of two strings, what do? Well, I write down the first character into the first slot in the output, and then I recursively do everything else. Except you do it in a for loop. You write down all the characters in the first string, and then you jump to the first case and say, oh, well, then I just write down the second string, which you also do as a for loop. So this is exactly what you are normally used to doing no matter what programming language you're in. All right. I do apologize, but that is the actual name of the language. It's important to be accurate. All right. So let me now try to do something simple. What is the length of the concatenation of two strings? We've got these two recursive definitions. One, how to glue two strings together into a bigger string, and the other is how to measure the length of a string. Let's combine them, because they're functions. That's what we do with functions. We make them call each other. What is the length of the concatenation of two strings? Yeah. So what I want to be able to do when I'm writing down proofs, I mean, this is an excellent question. We already know that this is well defined because we've defined the concatenation operation. It returns a string. And we've defined the length function. It returns an integer. So, of course, the answer is whatever that function returns. But when I'm thinking about proofs, I want to build up some intuition so that I can skip over some steps. I want to be able to express this in a different way so that when I see this expression in the middle of a proof, I can actually substitute it for something else in the middle of that proof. So having more than one way to say things is in some sense the one of the tricks in being able to prove things. The more different ways you have to say the same thing, the more you can look at a line in the proof and go, well, I can modify it without changing its meaning by doing this. I can modify it by changing its meaning by doing that. So I want another expression that's equivalent to this. It's the sum of the lengths, right? The length of football is the length of foot plus the length of ball. Okay? Great, that's intuition. We need to prove it. How do we prove it? Induction. Here's a hint. 95% of the time, when I ask the question, so how will we prove this? The answer is induction. Today it was induction. If it was induction in the previous lecture, it'll be induction in this lecture too. Let's do this. Now, I have a fairly unorthodox religious attitude about induction, which is it's the same thing as recursion, and so I should write my inductive proofs the same way that I would write a recursive algorithm. So let me finish writing down the thing that I want to prove. It's got a for all statement in it. Okay, so how do you prove universally quantified statements? For all strings, W and X, some blah, 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 blah. What's the first line of the proof? Even before you think about doing induction, what's the first line of the proof? I want to prove all snarks are boojums. What is the first line of the proof? Yes, let X be an arbitrary snark. Okay, so in this case, I'm going to say let W and X be arbitrary strings. When you're writing code, especially in C, this is in the declaration of the function, char star W star X. You declare the variables and you give them types. What's the last line of the proof? Well, okay, so QED, quod erat demonstrandum, that translates into English as which was what we were to show, which was what was to be demonstrated. What is it that we're trying to demonstrate? Let X be an arbitrary snark. Last line. Therefore, X is a boojum. Okay, so we choose an arbitrary item from our universe. Therefore, and then we prove something about the arbitrary objects that we picked out. This is where I have the first difference from the standard way that people learn induction, or many people learn induction. Many people are taught induction where you say, I want to prove the statement about all positive integers n. Great. So let me assume something about n and prove something about n plus 1. No. It's a universally quantified statement for all n. So I pick an arbitrary n and I prove something about that n, because that is the way you think about it when you're writing code. I'm going to give you an arbitrary integer and you do something with it. I'm going to give you arbitrary strings and you do something with it. I give you an arbitrary tree or an arbitrary graph and you do something with it. So this is the target. This is the thing we need to prove. Now, the second thing is, at this point, I sense, because I'm proving something about strings, and strings are recursively defined objects, I'm probably going to need to do induction. And so the big component that I need when I'm doing an induction proof is an induction hypothesis. Now, under the hood, every induction proof is equivalent to a proof of the following form. Suppose it's not true. I can suppose there's a W and X are counterexamples. Well, either I can prove directly that that's impossible, or I can find smaller counterexamples. Well, let me skip the reductio ad absurdum and just say, let me assume at the outset that W and X are the smallest counterexamples. What does it mean to say that W and X are the smallest counterexamples? Anything smaller works. So the induction hypothesis is always everything smaller works. Okay? Now, in this case, the induction hypothesis is assume for all strings y shorter than W, that the length of y dot x is the same as the length of y plus the length of x. Now, why didn't I say anything? I replaced W with a shorter string y when I did the induction hypothesis. Why didn't I replace X with a shorter string? Yeah. Yep. That's exactly it. In the recursive definition of concatenation, X is never broken. X is just this block that you carry around, and at the end you go, there. Right? I never open up that black box and say, oh, X has an initial character and the rest of the string. So when I'm dealing with concatenation, W gets opened up into A.Y, but X gets left alone. And so that's a good hint. It's not 100%, but it's a reasonable hint that when I'm doing my recursive argument, I'm probably going to open up W, and I'm probably not going to open up X. So when I open up W and I need to argue about its tail. Now I could have done this by structural induction and said, assume that if W equals AY, that this thing holds for Y. But a priori, I don't want to think that hard. I'm just going to say, smallest counterexample. And you'll see it again. You'll see this over and over again. Okay. Great. So I have an induction hypothesis. The next thing I need in an induction proof is cases. And the cases are really going to capture the definition of the object I'm doing induction on, which in this case is the first string W. So I'm going to say there are two cases. What are those two cases? What are the two possibilities for W? It's a string. So what are the two possibilities for a string? Right? So one possibility is if W is epsilon, and the other possibility is if W is, say, A times Y. You notice one thing that I really haven't started doing? Thinking. Everything I've done here, except for this business about exactly what should the induction hypothesis be, which even that you could put off until later, this is all purely mechanical. I know I'm proving something universal, so declare the strings. What is it I'm trying to prove? Oh, maybe I should read the theorem. Okay, write that down at the bottom. Oh, I'm proving something about strings. There's probably going to be a case analysis. Let's write the cases. Oh, it's probably going to be an induction proof. Let me write down something that looks like a plausible induction hypothesis. Mechanical, 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 mechanical. Don't be clever here. Just be thorough. Okay, so then I'm left with two pieces that I still have to fill in. And it's useful to sort of, when you're doing this on a whiteboard, remind yourself at this point what it is you actually have to prove. So in this first case, I need to prove that epsilon dot x equals the length of epsilon plus the length of x. And in the second case, I need to prove that the length of ay dot x is the length of ay times the length of x. Great. So let's start by giving ourselves some room. And now I will try to prove this first case. Now, the way that I would actually do this is I would say, okay, let's write down what we need, the left side of the inequality that we're trying to prove something about. Actually, I already know that this is epsilon dot x. And I'm going to write my way downward. And then at the other end of this chain of, I'm going to derive a chain of equalities that eventually is going to end in length of w plus length of x, and I'm going to work my way upward. Start with where I am and where I want to be, and work my way to the middle. All right, so let's start with this point here. Is there another way I could write this expression? The length of empty dot x. This is the same as the length of x. Why? Why is this the same as the length of x? Well, this is part of the definition of concatenation. Empty dot x is x. So right there on the label. So go back to the definitions. Great. Okay, I think this is probably as far as I can get to working my way downwards. Let me start working my way upwards. What can I say about this expression here, length of epsilon plus length of x? Well, yeah, the length of epsilon, what is the length of the empty string? 0. Great, so I'm just going to substitute in a 0 here. Fortunately, equality is commutative, so I could write it in the other direction. The reason for this substitution is by the definition of length. Actually, let me just write it explicitly. Definition of the length of epsilon. Okay, great. And now I have to somehow get from the second line to the third line. How do I do that? We all know how to do arithmetic. Okay, I can add 0 to any number and it's not going to change anything. And now I'm done. Notice the only thing that I did in this proof is substitute definitions. This is often how the non-recursive cases of induction proofs go. You just say, oh, by the definition of something, okay, by the definition of something, okay, by the definition of something, arithmetic, by definition, by definition, by definition. Okay. Right? So now let's work. Any questions about the non-recursive case? Yes. I'm sorry, could you say that again? You can think of it this way. So I do want you to notice something about the way the proof is now written. If you want to convince somebody else, which is the point of proving things, that w dot x is equal to length of w plus length of x in this case, you notice I've just written a series of forward implications. The length of w dot x is the length of epsilon dot x because w is epsilon. That's the same as the length of x by definition of concatenation. That's the same as 0 plus the length of x because you can add 0 to anything. That's the same as the length of empty string plus the length of x by definition of length. That's the same as the length of w dot x, the length of w plus the length of x because I assumed that w is epsilon. What I did not do is start with the left side and the right side and write down and connect at the bottom. People read text by starting at the top and working their way down. That is the direction that you should write, because you're not writing to convince yourself. You're writing to convince the grader. You're writing to convince the reader. Yeah? No. Write everything out. Never use the word never write LHS, just write it down. Or better yet, copy from the line above and paste it on the line below. Just make everything explicit. So your goal here is to communicate something clearly to another human being. Don't make them think. The first rule of clear communication is don't make the other person think. I'm in trouble. Okay. Except when you have to. There. And in this case, you don't have to. All right. So let's walk through the second case. We have a thing that we know. Okay, so we want to prove something about w.x. That's the same as a y.x. And we have a goal that we want to get to. That's a y plus x. That's equal to length of w plus the length of x. And now we need to figure out what we can, how we can connect the two ends. So working down from the top, is there anything I can do to rewrite this? And maybe this would be clearer. I just want to be absolutely sure that I'm not being ambiguous here, that the parentheses are around this. It's this string concatenated with that one. Can I rewrite that? Yes. So this is the same as the length of A composed with y concatenate x by the definition of concatenation. Right, so I can look back up at the definition of concatenation, and there it is. A is the first character, concatenation of y.x is the tail. Right? So this is using the sort of obvious fact that concatenation is associative. Football game is the same as football game, but we haven't proved that yet, so I can't use it. Can I rewrite that? Is there anything I can do to write this in a different way? Yes? Okay, so I could put the length of A separately and the length of y.x separately, except that's what I'm trying to prove. I'm trying to prove that you can do that. So it's a little dangerous to do that. But I already, in fact, know that I can sort of separate in the special case I'm interested in, which is the thing on the left is a single symbol, because I can look up here at the definition of length. W starts with a single character. I can pull that character out and turn it into a 1 and leave everything else behind. Right? So I can write this as 1 plus the length of y.x. Okay, I think this is as far as I want to go for now. Let me start at the bottom and try to work my way upward. Is there anything I can do to rewrite this expression in a form that might look more like this? Yeah. Right. So that length of AY is by definition 1 plus the length of Y plus the length of X. Let me make sure definition of length. Let me write down this again by definition of length. And now I need to close this gap between this green line and that green line. How do I do that? The induction hypothesis, hey, look, What did I assume? If I have a string y that's shorter than w, and I do have a string here y that's shorter than w, how do I know that it's shorter than w? By the definition of length. I pull the character off, the length goes down by 1. That means I can apply the induction hypothesis to this pair of strings y and x. And so the only thing I have left to write in my proof is the single phrase by the induction hypothesis. And it seems at this point I have nothing left to prove. I'm done. In both cases, I started with the length of w dot x, and I ended with length of w plus length of x. So in both cases, I proved the thing I wanted to prove. Clearly, the cases are exhaustive because there are only two things an arbitrary string can be, and I tried them both. So the end. Yes? Smaller length. Now, I want to preemptively ask a question that sometimes bothers students, especially if they've learned induction in a different form. Let's think about what happens. So let w and x be arbitrary strings. So in particular, w might be empty. But now the induction hypothesis is talking about all strings y that are shorter than w. There are no strings shorter than the empty string. How can I make this assumption about things that don't exist? Why is that okay? Okay, so one argument is the W empty case doesn't use the inductive hypothesis, and so the more traditional thing is to not even write down the induction hypothesis until the case that needs it. The reason I don't like that is because I don't know until I'm done which cases are going to need it. But I don't need to do that. That still, I mean, I'm claiming here that writing that induction hypothesis where I did, outside the case analysis, is completely okay, even though W might be empty. Yeah? Yep. Right. So this is the wonderful thing about the empty set. You can say anything you want about its elements, and that thing is true. Every single giraffe in this room is flying, made of chocolate, speaks fluent Mandarin. Every string shorter than the empty string satisfies that condition. I'm not actually, in that case, making an assumption at all. I'm merely stating a fact. You hand me a string that's shorter than epsilon, it will satisfy that condition. It will satisfy that equation. It will also satisfy the same thing with the not equals in the middle, because that's what negative length strings do. So in fact, it's perfectly safe to assume this because in fact it's true. The actual subtlety is what makes me think I can assume this when X is not empty. And this is where you actually need what's known as either the axiom of induction or the axiom of well ordering. This is sort of the formal basis of what makes induction work, is that you can assume no smaller counterexample for free as long as your recursion eventually bottoms out. Okay? So I'm going to always write it up at the top so that I don't have to think, do I need it in this case? Can I use it in this case? The answer, yeah, I can use it in whatever case I want. The other thing you'll notice here, I never used the word base case. I never used the word inductive case because I think this is a distraction. What you actually want is a case analysis that is obviously exhaustive. I need to consider arbitrary strings, and I have considered arbitrary strings. The definition of a base case is a case that does not invoke the induction hypothesis. But, okay, if I wanted to, after the fact, I could write base case, inductive case, but that's not actually providing any more information, so why bother? Okay. All right, so if you look in the lecture notes, you'll see similar proofs for a couple of other things. For example, concatenation is associative. Adding the empty string on the right side doesn't change the string. There's some other things that you'll see in the labs tomorrow, all of which are going to use the same style of induction proofs. And we'll see this over and over again throughout at least the first chunk of the course. If people have any questions, I'll be here for a few minutes and then out in the hallway. Thank you.